Hello, this is Venkat. Welcome to my channel. This video series is about a little pet project I've been working on to apply graph theory on a dataset. In this, I will start with a raw dataset, a list of stars, galaxies, nebulae, and other deep space objects for amateur astronomers. I will apply concepts of graph theory to extract relationships between the data and then provide a way to access the data via an API. I also created a lightweight HTML frontend to make it easy to access the data. I utilize AWS extensively for this, using services like AWS EMR, S3, Athena, and API Gateway. All my code is on my GitHub. The link is in the description. I'll be referring to it throughout the series. I am using these videos to explain design considerations and challenges I ran into along the way, and also to explain my thought processes as well as some of the alternatives I looked at. So let's get to it. So this is my raw dataset. It came from Astronomy Nexus. The link is over here. It has a list of about 100,000 stars and another 200,000 deep space objects. Those would be things like galaxies, globular clusters, nebulae, and others. It's a fairly extensive data set. It's got a lot of information, things like your catalog ID, the type. Very importantly, it has your right ascension and declination. Right ascension corresponds roughly to longitude, declination roughly to latitude, and that will give you the position of an object in the sky. Stars, very similar information. There's a catalog ID, you have spectral type, magnitude, and again right ascension and declination. So all of this is useful information in and of itself. But I was looking to see if there was a better way to visualize this data, and this was why I turned to graph theory. My thought was, what if I take this raw data and reworked it to look something like this? So this is the same data. What I've done is I've used the right ascension and declination in the original data set, and I've calculated the relationships between the data and the night sky. I have calculated things like the angular distance in the sky between these objects. So it would be something like, if you see a star like HD 150997 over here, I could view this naked eye without a telescope, and I would know that close to the star, about 2.5 degrees away, you have this globular cluster M13 from the Messier catalog. And I could tell you things like about zero point 0.4 degrees from M13. I have this galaxy NGC 6207, which is about 2.1 degrees away from the same star we saw earlier. And then you have this yellow star, which is about 0.3 degrees from both M13 and NGC 6207. I can also know that, hey, the other globular cluster, M92, is way over here, about more than 5 degrees away from this bright star. So this is a very useful way to represent the same data that we had earlier. It would be useful for people like amateur astronomers with backyard telescopes, such as myself. I frequently look at the sky using my telescope, and I frequently do this. I look for a star. I do something called star hopping. I find a bright star and then look at, hey, what could be the objects close to it. Or if I already have something in my telescope, like I might have M13, the globular cluster in my telescope, I would be interested to know that, hey, what is available close to this object that I could possibly look for in my telescope. And that is really the target audience for this database. And of course, there are a lot more nuances to graph theory than what I am explaining over here. The key challenge I was expecting at the start of the project was that if I needed to build out all these relationships, I would have a fairly extensive compute problem. If I started with my original data set of 300,000 records over here, and even if I restricted myself to 1,000 relationships for each of these data elements, I would still have about 300 million records for which I would need to calculate angular distance and direction and other things. So to solve the problem, I decided I was going to use Spark clusters running on AWS EMR to run the computation in parallel. So all my code is in my GitHub. And by the way, this is a more extensive representation of the data. There's a lot more data near M13 than just NGC 6207 and the star. There are a lot more galaxies and a lot more stars that you need the relationships between. So there's a lot of code on my GitHub, and the link to my GitHub is over here. Fundamentally, you could look at my code in two sets. I have a couple of files which I use to prep the data so that I can feed it into my Spark clusters. So these two files, extract, subset, and combine and create pairs, they combine the two files from my raw dataset into a single file, and then we create pairs of relationships, and that's just the relationships between the stars. So I would say M13 and everything close to M13, NGC 6207 and everything close to 6207. So I would create pairs, and that would be a very large data set. And then I would take my create pairs, the output of my create pairs, and feed it to EMR. So I would spin up Spark clusters on EMR. I would take my large set of records from create pairs, feed it to my Spark clusters, and the Spark clusters would be a multi-node architecture which would run the compute in parallel, and that is what would calculate angular distance and anything else I wanted on my pairs of data. Once I had done that, it was a matter of displaying the data for use outside the database, and the approach I took was to leave my data in AWS S3, and those would be CSV files sitting on AWS S3. I would query the data using AWS Athena, and then I would use API Gateway to expose my Athena queries via a REST API over the internet. And then I created a small static HTML frontend, which would allow me to query the data and retrieve it for use. So in a nutshell, that's what I have done. And over the next few videos, I will elaborate on what I said.